Hi everyone. This video contains the discussion regarding the days 2 through 4 analysis for the Pendulum Lab. That's most of the information. At the end, I'll talk briefly about the effect of gravity, something we didn't investigate, and then finally, to try to connect the last few weeks of work, I'll make some comparisons between the Simple Harmonic Motion Lab with the Mass on a Spring and the Pendulum Lab. You're all very familiar with the pendulum applet by now. This allows us to measure quite a few things. In all of our experiments, the period measurable by the stopwatch was the dependent variable. The first day of data acquisition, we investigated the effect of mass on the period, and you affect that by toggling this switch up here. On day 2, we investigated the effect of the string length, and that can be adjusted to any value here. And then finally, on day 4, we investigated the effect of the amplitude up to about 25 or 30 degrees. On that first day, we found that the period and the mass were not related. So as you increase the mass of the pendulum, the period remained the same. And so most people submitting the graph and answering the analysis question for that did show that there was no relationship. But be very careful here. This is the data that one person submitted, and this is the data that another person submitted. So while both of these people found that the period versus mass had no relationship, the actual value of the period that they were finding would vary. That suggests that one of the other variables that we held constant does affect the period, and that this person here had that value, had that variable set to a different value than this person here. The next day we investigated the period versus length. How does the length affect the period? As soon as you started taking data, you noticed that it was not like the previous day, and that in this case the length did have an effect on the period. So when we graphed that data, I'm going to switch over to the graphing program and run through that. And the data looks like this. Putting a curve fit, we really only have a couple of options. All of these on the bottom here seem to go in the wrong direction. Certainly squared is a bad option because it's not trending in that direction. And no relationship is obviously not true. So it's really between linear and square root. If people put a linear fit on this one, it is not a great fit of the data, and it really does not explain what happens as the length gets closer and closer to 0. For example, if we were able to set this value at 0.05, we would find that the value was far closer to this area than up here. So if we tried to get data in between these two, 0 and 0.1, we'd find that the data trends down here. And so for people deciding between that, our guiding question on that was always, what would happen if you tried to take data far outside of here where the data and the model would diverge, and what would happen inside of this, so smaller string lengths where the data itself could kind of come down here and the string lengths would diverge. Obviously we don't have that freedom, so we might just think about, does this intercept make physical sense? And it does not. It does not make sense to me that if there's no length to the pendulum, that the period is some kind of magical value of 0.6. So a far better relationship is the square root relationships, which does cause the period to go to 0 there. So this is the best fit of that data. And this just shows that graph with the data alongside. Now, taking this just like we did in the Mass on a Spring lab, this x to the 0.5 power is the square root. And x is not x is a placeholder for string length. And y is not y is period. So writing this gray box model for our system, it will look like this. And one really important thing is that everybody came up with this exact same result. So while there is another thing that affects it, it must have been the same for every person. We'll talk about that in a little bit. Period versus amplitude was our last one, and we specifically asked you to limit it to less than 30 degrees, so anywhere between 0 and 30 degrees. And when we did that, same thing, the amplitude did not change. Now, again, you guys know string length affects it, so what your actual value was depended on what value of string length you chose. So people using a longer string length and investigating this, they held string length constant, but if it was a longer constant value, they would have a larger period. So now, really important here, we would show that there's no relationship, or we would conclude that there's no relationship here. But if I kept taking data, an interesting thing happens. Beyond 30 degrees, this period starts ticking up a little bit. And if I were to graph that, here's the original data from 0 to 25, and then when I get to almost to 40, it starts going up a little bit. And the reason for that is that a pendulum really just is a little different than a mass on a spring, and that the restoring force is not exactly linear in the way that a mass on a spring is. So it sort of diverges from that behavior out here. That's not going to be a big subject for us, but that's kind of why that happens. Now, this is a little bit extra right here, and it's just, I'll talk for about 2 minutes regarding this. And if you find it a little overwhelming, then that's just going to be okay. This is not something that we have people account for. But I think an interesting idea here that some people noticed is that you can change the gravity to different planets. And so one thing that emerged on the first day is something interesting that I want to tell you guys about. So on that first day discussion, when we asked if anybody noticed anything, cool about the features, a lot of people talked about, the things that we then investigated, but some people talked about these two, and they said you can actually affect the gravity. So, and what they found was, not only can you select other planets, so if I go like this, and then in the middle of that, all of a sudden switch it to the moon, I could see a noticeable slowdown, right? If I switch it to Jupiter, and then interestingly, if while it's going, I completely remove gravity, I no longer have a pendulum. So within the absence of gravity, this thing just keeps going around, which suggests that gravity is a factor, and gravity is something that we did not investigate but does affect it. If we had investigated it, we might say, what is the gravity strength, which we call G? And you guys know about G on Earth, which is 9.8 newtons per kilogram, and this is the period we would get for whatever string length we decided. And the other two planets we can use are the Moon and Jupiter. So what I did is I looked up the G on the Moon and the G on Jupiter and actually used the program to record the value. And I found this graph. And so what was interesting to me about this graph is this is kind of that same inverse square relationship that we found when the mass on the spring, we found a similar relationship when we investigated the effect of spring constant on period. So pretty interesting. Again, this is not something you guys are really going to be forced to use in an equation sense, but it is an interesting idea related to how a pendulum operates. So you could write that math model. Again, not something we're going to do, but that's where G would go. So just the Pendulum Lab Summary really quick. Period is not affected by mass, increasing or decreasing the mass, same period. Period increases with string length, but it is not linear. It's proportional instead to the square root of L. And for all of us, we got this relationship here. Period is not affected by amplitude, and that was true at low angles, though we saw that diverge a bit. And then finally, period decreases with gravity strength. The stronger the gravity, the lower the period. And if we really investigated it, it would be that, but we don't do that. So in general, if I looked up the period of a pendulum, it would look something like this. And we've seen this before because it's very similar to the period of a mass on a spring, and I'll make that comparison. But this would show that the period of a pendulum is proportional to L. That's something you investigated and know. It would also show that it's proportional to this. You'll notice that amplitude is not in the equation, and that's something you investigated. Amplitude's not here. And mass is not in the equation, another thing you investigated, and that is not here. Now, how does this translate to what you guys discovered? Well, if all of us are on Earth, then this g is a constant, and we can rewrite this by bringing it out here. And so the only variable really is L. And if we replace that g by 9.8, then this value here, 2 pi divided by square root of 9.8, is 2.01 square root L. So this is why, because g is a constant, and we can combine all these, this is why everybody got that same relationship. We can use that relationship, and that is the relationship you're going to be asked to use, that simpler one. So if we use a mass of 0.2 kilograms, predict the period when the string length is 4 meters. Now that's way outside of here, and this is not something that was allowed by the program. First of all, it makes no difference what the mass is, so that's not going to incorporate. That's just almost like distracting information. But what we can do is use this expression, which we will ask you to do in the coming week or so, and we can plug in our value of L. I'm not going to deal with the units either. This would be length in meters, and this would be period in seconds. So if I put in 4 there, obviously that simplifies. Square root of 4 is 2, and the period of a pendulum is 4.02 seconds. We could go the other way. You'd like to make a pendulum with a period of exactly 0.75 seconds. How long should you make the string? Use the same equation. Your period is going to be 0.75 seconds, not dealing heavily with units, just introducing the idea. Then solving for L, dividing both sides, squaring both sides, and we find that the length that produces a period of 0.75 seconds should be 0.139. Well, let's see if that is a good prediction. So going back to our program, we can switch this down, and we can use I think we can, 0.139 would be about right there. You know, it's right 0.13, this is basically 0.14 or 0.139. So we can get this thing going. We know it doesn't really matter what amplitude, so I'll just get it going here. And then I'm going to do 10 periods, right? So I'm looking for this to go start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And look at that, 7.5 over 10 periods would be 0.75 seconds per oscillation. So that's great. It's an equation that works. We can use it to predict how long the string length would be to make a specific period. So what we want to do is quickly compare the equations that we've learned over the last couple weeks. On the one hand, the mass on a spring, and then over here, the period of a pendulum. We see a very similar structure, the 2 pi, and then the square root of something over something. So in the mass on a spring, that thing right there that makes the period longer is mass. Why does the mass make the period longer? I think you have some idea of that. The thing that makes the period longer on a pendulum is length. How does the length make the period longer? That's actually a really challenging question, so I won't ask that one. But if you would like to learn more about that, perhaps an advanced physics class, and we can talk about that. It looks like on a mass on a spring, the period that the factor that makes the period shorter is the spring constant. Why does the spring constant cause the period to be shorter? And then for a pendulum, the thing that causes the period to be shorter is the gravitational field strength. So I'll ask you that question. Why do you think that the strength of the gravity makes the period shorter? If we have more gravity, it makes the period shorter. Why does mass appear over here, but not over here? Why does amplitude appear in neither one of these? These are all good questions, things you could answer. So your questions today will be a couple of those, and you you could comment on them. So thanks so much.